So this is a quick journey through the audio system, which is a bit of a jungle, as anyone who's ever had a look into it. And I had the unfortunate experience of actually going in and getting lost in it for a period. So let's just quickly go through, so I don't get too lost in the talk. The purpose of the talk is how does game audio work, and what's it do, and then that's a distinct thing from what's the implementation in Godot, because every game engine has a different sort of implementation. And then also how any of you guys can contribute to it and sort of what direction we might be trying to take it in. We being whoever's showing up at the Godot audio meetings or whoever does pull requests, really. So about me is I'm definitely not an audio expert or a musician or a sound artist. I really don't belong here. I'm more of a mathematics and CNC machine tools. But what happened in about 2020, I got a strong interest in VR and did a whole bunch of Godot programming back then. And then quickly realized that networking and multiplayer was absolutely essential in VR because you've just blindfolded your players. And so you can't, you've separated them out in the way that they aren't if they're actually working on a normal screen. And then also discovered VR chat last year, and I'll mention that in a moment. So this is an example of one of the projects I did using Godot and showing the multiplayer off. Is that you've got a sort of wind tunnel simulation, and I had two engineers in it, sort of both showing each other and pointing out little sections of the wind flow in it, and that kind of showed how the multiplayer was so important. Then last year I played far too much VR chat and went from a kind of lonely guy to having loads of friends. And it kind of changed my life a bit. I keep finding unlikely Godot core maintainers in VR chat now and then. But one thing we do want is this is all based on Unity, and we'd kind of like to have this tech in Godot. And one of the core things you're going to need is voice over IP. Which we don't really have. And so that's kind of where I started work to try and make my little contribution. Now, the problem was over the years, we discovered there were two really severe bugs in the microphone system, and there was a really broken area in the spatial audio that nobody noticed. And it's kind of the story of these sort of shows you how much jungle and weeds there are out in the audio system to be found if you know what you're looking for or you really want to find them. So if we just go through how voice over IP works, it's relatively simple. There's a library called Opus that compresses it, and you kind of take a 20 milliseconds chunk. You want to just think in audio, just think in terms of just arithmetic and frames. You take a 20 millisecond chunk of the audio at 48 kilohertz, and that adds up to 960 frames. So they're calling a frame one little sample that's going to the speaker, kind of like video, where it's 60 frames a second. We have a lot more frames, but they still call them frames. And then that's 960 for 20 milliseconds. You have to double up because it's stereo, and it's just an array of about 2,000 floating point numbers. You drop it into this compression, and it gives you 30 bytes out. You ship that across the network, and then at the other end, it unpacks it and goes to the speaker. And that's kind of like the basis of it. The reason it can compress so well is because this, just the same with compressing video, the sound in one 20 millisecond chunk is pretty much the same as in the next. So you only need to send the differences, and that's why it's so effective. So pretty quickly you start finding that there was really bad bugs in it. One particular one, which took a while to find, was it was broken in Linux. Reported in 2019, it was broken, and then I kind of noticed that every other 4-point release it would work, and then the next one it didn't work, and then it worked, and then it didn't work. But obviously no one considered it a blocker because the releases were going out. So I contend that meant no one was actually using the microphone, because the only purpose of the microphone is for voice over IP. So if there's no voice over IP, no one needs the microphone. So when I was debugging one other bug, I found that just the change of one print statement made it work or didn't work. And I've seen one of these things before. It was essentially an uninitialized parameter in the setup, and it either gave you a little buffer of 4 bytes long or 40K long, and depending on what kind of garbage the compiler stuck into that parameter, it worked or didn't work. And that was one of those satisfying things where the PR was merged in about 11 hours from committing. So things move quickly sometimes. Now, let's just recap what sound is really going on. So in the real world, you've got sort of sound sources shaking around and waves going all over the place in 3D, reflecting off things, resonating against other things, and then you pick up the sound at the other end, which sounds a bit different from what the source was. And you kind of perceive the ambience of it in that way. Now, in the game engine, we don't quite have that, because obviously if you just played the sound source, which will be like a MP3 play or a WAV file, straight into the speakers, it's going to have crystal clear reception. And we don't really want that, because you want things to go quieter when they're further away, maybe get a bit muffled when they're behind a wall or something. And so what we do, if I'm assuming some familiarity with the with playing with the sound in Godot here, and by the way, if none of this makes sense, or some of this doesn't make sense, you can find me afterwards, and I'll go through it in more detail. But what's happening is the sound goes from the audio stream into an audio stream player, and that sort of measures the distance to a listener and adjusts the level of the sound on the left and right ears, and then feeds that into an audio bus, and then the audio bus has some effects. You might add a little bit of echo or reverb or something, and then eventually goes to the speaker out. And that's sort of simulating all that kind of crazy wave stuff, or trying to give the impression something's going on there. So let's just now get to some right down at the very bottom level of the code. So game audio is at the very bottom level, very simple. You just have a sound card which wants to have a set of floating point numbers measuring the sort of the position of the diaphragm in the speaker at a certain rate. So there's this real-time system consuming positions of this speaker, and the interface to them is usually some kind of weird thing where you've got because threads, we don't really know when they're coming or going. So what the interface in, say, Linux is you just throw a buffer in, and then the real-time system says how many frames it's taken out of that buffer, and then you kind of like shift things around and keep doing it over and over again. As long as you do it fast enough, you can keep that buffer full. And what this then means is, let's see, okay, let's move straight on to the next bit. What this then means is that you then have to have, the Godot has to have its own little mini buffer, which is keeping the sound card buffer full, and then using that to call up into the main audio system with chunks of sound that it's going to like triage between going out and calling back into the audio system. And that's one of the settings that's in project settings. You'll look it up. It says what's the latency, and that's the default is 15 milliseconds, and then it kind of decides a buffer which is in a little function which is about 512 frames, and so you actually get a latency of 11 milliseconds when you put that in. Now that function right at the bottom has a little process in each of the different platforms, and then that calls to a process higher up in the audio server. Finally, we've entered the audio server, and the audio server has one function, one critical function called mix step, which is the thing that gets the entire thing that you see in the Godot game with all the buses and all that stuff, which, as we know, feeds into the master bus. And then after it's fed to the master bus, it then grabs the 512 samples from the master bus and then delivers it down into the sound card level and all those interrupts. So this is where the monster is. So this is a gigantic function. When you can page through it, it just never ends. So in this single function, so I was talking to someone last night, and they came to the same conclusion as me. As it was like the whole thing was written in a couple of weekends, very quickly, and then no one's really looked at it since. The audio system is quite sophisticated in a lot of ways, but little sections of it have been left broken because no one actually went back and debugged them. but that's kind of adds this complexity. So this one function loops over all the buses. It then handles all the effects on each bus. It then calls out to all the audio streams and grabs the sound from each of the audio streams. It then also has to loop across the channels, and that's also confusing because there can be up to 4 channels, and you think of a channel as being a left and right speaker, but channels are also used for the four channels for surround sound. I'll show you a picture of that in a moment. And then there's also an extra little tweak that makes things really complex, is that there's a fade out. Whenever one of the sounds is paused or stopped, it has to taper it down, otherwise you'd hear this click. And that kind of, as you'd imagine, is all inlined buffer messing up, and code that should have been much simpler winds up being very complicated. So this is one of the surprises that came to me once when I was debugging stuff, is sometimes the bus layout looks like this. If you happen to plug in a set of speakers or a surround sound, then Godot quietly goes and just doubles everything up or quadruples everything up like this when you're used to the thing on the left. And this caused a lot of trouble because no one ever saw that before. And this also meant that whenever anyone was debugging or doing changes to the audio system, they never saw that feature. And so that feature would often get broken since it wasn't tested. I still haven't found anyone who actually uses a real surround sound system. What the surround sound systems, every time I've actually pestered someone and got the details, it's usually something feeding into some surround sound headphones, and they've got a driver that down mixes it back to 2 speakers. So I don't see why we can't get the sound good right in the first place. So the other thing that's also terribly confusing is you have these multiple mix rates. You've got a mix rate from the input, and then the mix rate going to the outside, and you've also got different mix rates for the streams, for the WAV files, and it can be confusing why there are. I was very mixed up why it was all different numbers here, and I think I can explain that near the last slide. So to see how far we've got, okay? So exactly. So while I was, I'm not talking about one of the microphone problems, but while I was trying to explain why I wanted to fix the microphone in this way, I did this gigantic diagram of what was going on in all the different levels. So we have so far mentioned the green box in the top level, and then those 2 functions inside there, and now we've got to the mix step. And it's the mix step that's looping across the audio bus and looping across the streams and then delivering the stuff outside. We don't need to talk about the microphone things. So let's now get to the buses and effects. So this is at least fairly straightforward. Is that each bus has a 512 sample buffer, or about 11 milliseconds, approximately, close to that latency that was programmed in the project settings. I don't really see a reason why it's got to be a power of 2, because these are actually quite small samples. So, yeah. So the frames are there's just a float left, right, and you've got a set of effects on each channel and in each bus. So in diagrammatic form, it's a little easier to look at. Is that you've got the audio streams are feeding in their 11 millisecond chunks into each of the buses they've been pointed at. And then what it does, the effect is like the definition of the effect instance. And, so it's got the numbers, whereas the effect instance has the actual implementation and the buffers, although sometimes they get a bit confused in some people's code. Certainly my code, I messed up, I mixed them up quite a bit. So what then happens is we start with you'll notice that when you're connecting buses, you can only feed buses to the left. So if you start processing the buses from the right-hand side, well, whatever, the right-hand side all the way to the left, then each as you take the frames through all the effects and then add them to the frames on the next one. They call that mixing, but it's basically just taking the floating point numbers and just adding them side by side into the next array. And then eventually you get to the final one, and that gets sent down to the sound card in the mixing thing. So I wanted to go through an individual effect. Oh, well, yeah. Oh, yeah. Oh, great. Okay, I wanted to go through an individual effect. So here's some nice, unhelpfully confusing code, but the idea I want to get across is that an effect is kind of like we're used to GPU shaders, where you have little tiny bits of code that do amazing stuff in the graphics. And effects are kind of similar, where there's a tiny little bit of C code that does usually quite sophisticated things. And one project would be really nice would be to make these things compilable at runtime, so that people can like start tweaking them sort of in-game or as we do GPU shaders. And it would be really lovely if someone went down that rabbit hole and started producing some quite amazing effects in the way that they do with shaders. So this particular effect, all we're doing is we're just taking the sound, recording into a little ring buffer, and adding on the sound from a delay. So diagrammatically, it just says we just take the waveform like so, shift it across a little bit, and add it on. Implementation terribly simple. But has quite complicated effects. So to give a little idea of what we're talking about in terms of the effect, let's just take an example of just doing it with a sine wave, your pure frequency. If I take one sine wave, and then I sort of shift it across, maybe change its amplitude a little bit, and then add it together, all you do is you get another sine wave in between. And so in some sort of mathematical sense, at every single frequency, there's only one thing happening. There's only one sine wave, and which has a phase and it has an amplitude. Nothing else is going on. This is kind of similar to what happens in visual thing, where when you shine lots of different colored lights onto one spot, you only perceive a single color there. I mean, it's not true, because there are actually colors in there. But your brain is just processing it as a single color. In this case, you're getting a single wave. It's not the same. This is mathematically true, that when you combine waves of the same frequency, you still get just one wave that's still simple. And that's kind of the basis of all of hearing, which I'll mention in a moment. Let's see. So that particular effect, if we were to model it, is we're just a delay of 50 frames. You know, you want to do your sort of arithmetic. 50 frames at 44. I was going to sing it. I'm not going to sing that tone. Is about 100 frames. And so if you add 50 frames across, then the waveforms exactly cancel out. So, and that's sort of the same as if you had a wall that was about 19 centimeters away and the sound reflected perfectly from it, then certain notes would just disappear. And that's from the simplest effect that you could possibly make. So, you know, imagine what you could do with other ones. So let's see. So this then sort of leads to a little diversion into what hearing is like, because I had to learn all this myself, is that the way we hear is that the inner ear measures the intensity at each frequency using this little organ, which looks like a snail. But the critical thing about the ear is that at each cross-section corresponds to a particular frequency. And at the cross-section, you wind up with this sort of structure. And you have the membrane at the top, which is vibrating of that particular frequency, and it's got a little tuft of hairs, and depending on how hard the vibration is, it hits more of the hairs or fewer of the hairs, and that's kind of like gives you your sense of amplitude of the waveform. But then even more crazy is there's these extra hairs on the outside, which are motor hairs, and they can sort of move the membrane up or down or make it slightly less floppy or something, and they can adjust. They can basically tune how sensitive it is to a particular wavelength. And so your ears can basically have this living graphic equalizer happening in real time. And that's kind of like how when you adjust your hearing to listen to one sound over another one, your ears do actually change inside, sort of in the same way as we're used to our iris changing in the eyes. There's also a huge amount of research on it. If anyone wants to page through this book, we've got. You probably notice that when you have certain frequencies, even if you set the decibels to exactly the same, certain pitches sound much louder than the lower pitches. Well, there's reasons for that. You can do it experimentally on the right, where you get people to say, does that sound the same volume as that? And they can graph it or something. Or ones where you actually stick a microphone right inside the eardrum and you play a sound in the front, and actually this certain sounds carry through into your ear in the way that others don't. And so this sort of tells you that it's going to be very different if you have a speaker in front of you versus if you have headphones with the earbuds going straight into your ear canal. You might want to do something different there, or think about it. So we've nearly got to the end, I guess. So we've done the mix step. So we've done the buses and looped over all the effects, and now we're going to do number 3, which is the audio stream playback, which is where a lot of the real confusing bits happened. Then there's the channels and the fade out, which I'm not going to go into the fade out. So here it is, all in one diagram, the audio streams. And the problem is that there's an invisible layer inside the audio server. So when you have a look at the audio stream playback, it's got all these extra little things like the emission angle. Okay, so what it's going to do is if something is playing out in a particular direction, you're going to have it. You're going to sort of model it being quieter if it's playing away from you versus if it's playing towards you. That just changes the volume. But there's also this attenuation filter. So attenuation just means making it quieter, and it says if something's far away, we're going to make things quieter. In the higher frequencies, and that's kind of this effect that if you have something like 2 kilometers away and playing really loudly, you just hear the bass notes through. You don't hear all the high pitches. That's built in to the games engine, but hard to find. So let's just work this out again. So we have the 512 frames that are going to be added to the bus, and that's pulled from this internal node called the audio stream playback node. And that goes and pulls the 512 frames from the resampled. So this is where the sampling happens, is that the audio stream or MP3 has its own frequency. So it'll run it at, like, say, 48 kilohertz or 192 kilohertz or something, whatever it's been recorded at. And there has to be this sort of resampling of it so that it's able to be compatible with the sound card that you're going out. And that all occurs in this one place where it pulls in about 128 frames per cycle, adds it into a little buffer, and it doesn't just interpolate them linearly. It kind of like fits a cubic spline to it and then resamples it so that things are kind of smooth. And since you're doing the resampling there, all the changes of pitch all occur in this one function. So your Doppler, that feeds in and adds into multiplies into this value. There's the rate scale, if you can program that in, that also feeds in. And so you're requesting 512 frames out, and 1,000 frames are going in at the other end. So your pointer along the audio stream is going to be moving a lot faster. And then there's a mysterious playback speed scale, so you can change the speed of all the sound all across the whole game at the same time. I have no idea why anyone would want that. So anyway, so after it's fed that through, it then gets into the playback node, where this is where the sound levels on the left and right ear are set, and also the filtering. And that's all hidden away. And this is where there's also a little bit of a confusion, where the audio stream player looks like 3D looks like it's part of the audio system, but it really isn't. All it does is just have a look around the environment and then update the little parameters inside the playback node to say, well, you need to change the volume of the left speaker to 50% and the right speaker to 100%, and it just updates that on another loop. So that led to another really horrendous bug, which sat around for about 8 years. No one spotted it. And it was one of these things where people said, "Oh, Godot audio is a bit crappy," but you need to know what's going on. So the thing what we expected is if you put a sound exactly, if you turn up the panning maximally. If you put a sound exactly to my left, then I'll have 100% of the sound on my left ear and 0% on the right ear. And when you're straight in the middle, it'd be 70% each, and so forth. And it wasn't coming out right, and I eventually wrote a program that would spin the sound source around and then plot it on this polar graph, and I found out it was completely messed up. And the actual, if I played the sound at 45 degrees back to my left, that was when the sound in my right ear was 0. Right, that's kind of like what that's showing. And then to prove that this was definitely not what anyone wanted, I sort of replicated the thing in Unity, printed out and plotted it and showed this is the way it's supposed to be, and eventually got this pull request in. So the key thing is don't ever trust your ears on these things. Always convert something into a graph, and then you might see what's going on. So I think we're getting finally. Because it's not about my bugs. This is we've got a sort of audio group meeting going about every 2 weeks, and here's someone who comes along to most of them, and she doesn't say much except that she can't code C++ very much, and then makes these amazing pull requests that fix about 20 different things all at once. You're probably going to notice this as well, because stuff like the audio bus, when you when you put your cursor over it, it writes the value across the right-hand side, and she's changed it to go onto the left-hand side. It made it much more beautiful and cleaner and stuff. And she put that one in, and before we even got time to actually discuss it, it got merged. So there are other people, other parts of the game engine, not just the audio. They're paying attention and doing stuff. So there's a lot of scope for doing some amazing stuff in here, if I can encourage you to do it. And so the future directions are pretty much audio group meetings every Tuesday. Every other Tuesday, anyone can come along, find the invite links in the Rocket chat. We're gradually working through the backlog of audio pull requests and set up a triage so we stop losing things like 2 years out that people actually want us to look at. It'd be lovely to be able to regularize the audio server so that it can be swapped out in the same way as people were able to swap out the physics server for different physics engines, because then if you could swap it out, you could do some really amazing stuff, have it as a plug-in, and then people would like that, and then we'd swap it in. You wouldn't have to fight over every single little feature. Excuse me. And another important thing is the audio stream player probably wants to have its own little effects bus in it. No time for that. And what I also would like to see is a sort of playground project, some demo project which has all the different little audio playgrounds and effects and stuff that bells and whistles that you could tweak around with, and then that would be the go-to place for finding bugs or showing what the power of it is, and so forth. And I guess that's me, right?